Hello everyone and welcome to the week 5 of NPTEL course on pharmacognosy and phytochemistry. In this week we are going to dwell on a set of very potent natural compounds, and those are alkaloids. Alkaloids, as the name indicates, are alkali like compounds which are found in nature, and their alkaline nature is attributed to the presence of nitrogen. So, alkaloids are defined as naturally occurring nitrogen containing organic compounds found primarily in plants but also found in some other organisms, which includes bacteria, fungus and some animal species. Now here, because they are alkaline in nature, the nitrogen is mostly in a negative state of oxidation. If you consume them, they are intensely bitter and majority of them are pharmacologically active. So they are very potent class of compounds as compared to other class of phytoconstituents. So just giving you some examples of alkaloidal compounds around. So if you see your beverages, especially tea and coffee, you might have heard of a compound called as caffeine. So caffeine, which is present in your tea and coffee, is an alkaloid. In your chocolates, you will find your compounds such as your theophylline and theobromine especially. And if you heard of an anti-malarial compound called as chloroquine, it comes from a compound called as quinine, and quinine is found in cinchona bark. Cinchona bark was originally used by the Jesuits to treat malaria, and that's where the genesis of your chloroquine, which is a famous anti-malarial compound, is. Now owing to evolution and owing to more potent drugs, chloroquine is declining in its usage but still makes up a good role model to study the evolution of your drugs coming from nature. So if you see alkaloids and if you see the clear definition, alkaloids are nitrogen containing heterocyclic compounds and are known to have their genesis from amino acids as a biosynthetic pathway. So when I am talking of alkaloids, I could principally divide them into three classes. The first class would be true alkaloids. The true alkaloids are the ones which have both of these factors incorporated in them. That is, the nitrogen is a part of heterocyclic ring, and secondary, in terms of their biosynthesis, they are derived from an amino acid biosynthetic pathway. To give you an example of alkaloid which is a true one, you can see your morphine. So here it is, morphine. Morphine is given as a analgesic, a painkiller, and is also used to make a lot of banned substances. Now coming to the next compound, and that's your pseudo-alkaloids. Pseudo-alkaloids are slightly different from alkaloids in a way that they have nitrogen as a part of heterocyclic ring, but in terms of their biosynthesis, they are not derived from amino acids. So in that case, you have an example of caffeine. Caffeine generally comes from your xanthine, and that's do not have a clearly what is called as amino acid biosynthetic pathway. The third case is a case where actually your alkaloid is derived from amino acid. As you can see here, in mescaline, the nitrogen is outside the ring. So here, despite being derived from amino acid, it is no longer a part of heterogeneous ring. Such cases, these alkaloids are called as protoalkaloids. An example of this is mescaline, which occurs in peyote cactus or Sao Pedro cactus. Now this cactus species are endemic to Ecuador and Peru and South American countries. So during the desert, this cactuses store a lot of water as well as alkaloidal substances. So people, those who consume this cactus while consuming or once they are thirsty, they tend to hallucinate, because this has psychedelic effects. So mescaline is one example. Another example is your conicin. So if you see alkaloids are very potent class of compounds. They have effect on CNS like caffeine, mescaline, or even they have anti-inflammatory, analgesic. In the subsequent lectures, you will see lot of other potent effects of alkaloids. So just a brief once again, true have their biosynthesis from amino acid pathway as well as nitrogen in their heterocyclic ring. Pseudo do not have amino acid biosynthetic pathway, and proto have their nitrogen outside the heterocyclic ring. Now, what role do the alkaloids play in nature? Alkaloids, being potent, are very defensive and help get rid of herbivorous animals and insects. I'll give you an example, an interesting one. So, if you're a Harry Potter fan, you must have heard of this Wolfsbane potion. That comes from alkaloid containing plant, which is your aconite. Now, aconite roots have been used as poisons, so much so that they've been applied to arrows to kill the animals. At the same time, if you are trekking and if you come across aconite flowers, if you just tend to touch them, your hands will turn numb. That is the level of potency this compound have. And we all know the potency of nicotine. Nicotine is present in your tobacco and is known as a CNS stimulant. But also, if you know the advantages of nicotine, the tobacco has been traditionally used as an insecticide and pesticide because it produces the same effects in insect, but insects do not tolerate it. So that has a lethal effect on insects. Now it also protects against certain microbes. They are very good antimicrobial. They carry out the process of allelopathy. Allelopathy is a process of mutual suffering where you will see a plant, especially the one containing alkaloid, will not allow the other plant in its vicinity to grow and flourish. So this plant will synthesize alkaloids which will leach in air, which will leach in soil. They will reach the next plant. The moment they reach the next plant, what is going to happen is the next plant is going some kind of growth. This happens through numerous processes. These growth processes are hampered and the plant stunts in growth and eventually withers and dies. So it has a role to play in plant growth and development. It plays a vital role in repulsion of pollinators, or even in some cases even attraction of pollinators, and it's a good source of storage of nitrogen. So these are the vital functions of alkaloids in plants. Now if you see properties of alkaloids, they are alkali like, they are basic in nature, and if you see in terms of their molecular properties, they are mostly crystalline except nicotine, because nicotine is liquid and at room temperature, and emitin, if you see, is amorphous, not crystalline. Most of the alkaloids are colorless, but again there are exceptions such as berberin, which is a little yellowish, and betanidine, which is slightly reddish in coloration. In terms of its basicity, because they are nitrogen containing, mostly they are basic in nature. But what happens is, if this nitrogen is surrounded by something, let's add little chemistry to this. So if nitrogen is surrounded by a functional group which is electron donating, that increases the basicity of your alkaloid. But imagine if your nitrogen is surrounded by something which is electron withdrawing. Say for example, your nitrogen is surrounded by a carbonyl. So in that cases, they tend to be more neutral or acidic. They lose their basicity. So if you see your piperine or if you see your colchicine, in that case they will not be basic, they will be more of a neutral compounds because of the electron withdrawing neighbors that they have next to the nitrogen moiety. Now most of these alkaloids form water soluble salts. Now alkaloids may be present in their native form as nitrogen containing compounds, but what happens is, owing to their basicity, they attract a lot of acidic compounds and tend to form salts. Now they may attract some organic acids, oxalic acid, or in some cases very specific acids such as meconic acid, quinic acid and so on. So, this conjugates occur, even alkaloids tend to form associations with tannic acid because they are basic and tannic acid is acidic in nature. So, they occur in plants as such, or they might occur in form of salts. When they occur in form of salts, the salts are generally water soluble, except a few cases. Take for example quinine sulfate, which is a water insoluble salt. Now, let us see structurally. Now, structurally also there is a huge difference between the alkaloids. Some alkaloids, the nitrogen occurs or takes form of primary amine. So, if you see here norephedrine structure, the alkaloidal nitrogen, definitely it is a proto, but acquires a primary amine functionality, whereas if you see your ephedrine, now what happens in ephedrine is one of the hydrogen gets replaced by a methyl group. So, these are the both isomers of ephedrine. So, in this case it acquires what is called as secondary amine structure. Now, it might or they might also occur as tertiary amines. Take a case of atropine, which is there in your belladonna or atropa belladonna, and this is also there in some case of your local anesthetics such as tropane. So, you will see a nitrogen here, and the nitrogen here is a tertiary amine, and in some cases they also have a quaternary character. A good example of such cases is your tubercularin. So, if you see a tubercularin, it forms association with 4 atoms in its vicinity. As a result, it acquires a net positive charge and we call that as a quaternary amine. So, alkaloids may occur as primary, secondary, tertiary or quaternary amines. Now, alkaloids also occur in different isomers, stereoisomers. I am just giving or pointing out at 2 examples of isomers and how they affect us. So, let us take a case which is discussed cinchona, which contains your quinine. Now, if you see cinchona, it just not contains quinine, it contains numerous other alkaloids. These alkaloids are quinine, quinidine, cinchonin and cinchonidine, just to put you or give you 4 examples. Now, of this your quinine and quinidine are stereoisomers. So, if you see here, they differ in their isomerism principally at the 8th and 9th, but I am not putting this hydrogen into perspective. Just see the hydroxyl. It is different here, and why this difference matters to us is quinine is pharmacologically antipyretic molecule. So, it helps in malaria, it helps you decrease your fever, whereas if you see quinidine, quinidine is a molecule despite being stereoisomer has much lesser or negligible activity as antipyretic, but it is more famous as an antiarrhythmic agent. So, it is used to treat heart disorders such as arrhythmia. Same is the case with ephedrine. If you see your L isomer of ephedrine, the L isomer of ephedrine is almost twice as potent as D isomer of ephedrine when it comes to your nasal decongestant effect. Now, let us see how do you detect alkaloids. Now, alkaloids are nitrogen containing compounds. We saw that they do not fit into a particular law. When I said basic, there were exceptions. When I said crystalline, there were exceptions. When I said primary amines, you saw also there are secondary, tertiary, quaternary amines and so. So, to put alkaloids in one box is a difficult thing, but there are few chemical tests which can help us assess if the plant contains alkaloids or not. Now, when you are detecting alkaloids, you are basically detecting a nitrogen group. Now, in addition to alkaloids, there might be proteins in the plants which might interfere with the detection. So, what is done in this case is we know that proteins are not soluble in alcohol, and that is precisely the step that we use. what is done is the plant extract or the plant part is taken. This plant part is basified. The reason being, if you think of a salt or alkaloidal salt, we saw that alkaloidal salt is water soluble. So let's convert it into a free base, and for converting it into free base, you add a little base. So take your extract or take your plant material, convert it into a free base by adding alkali, and then this free base, because of its unionized nature, has more affinity to organic solvents. So in this case, what we can do is, rather than extracting it with water, which will extract your proteins as well, let's extract it with alcohol. So an alcoholic extract is taken. Now the alcoholic extract doesn't contain protein, and whatever nitrogen is detected chiefly because of alkaloids. Now this alkaloidal nitrogen has a good affinity to form colored complexes or precipitates with iodine. So different salts of iodine are taken. They called as different coloring agents, and their ability to form precipitate with this nitrogen containing compounds form the basis of most of the chemical tests. So the alkaloids or the alcoholic extract of these plants can be reacted with Dragendorf reagent, which is potassium bismuth iodide. In this case, the color complex that we get is a red color precipitate. Or with Mayer's reagent, in this case, what is used is a potassium mercuric iodide. So you will see iodide is a common entity in all of this. So it will form a pale yellow to whitish precipitate. Hager's reagent is again detecting your amino group, and it's your picric acid. It reacts with amine groups to form a yellow color precipitate. One more iodine containing reagent is your Wagner's reagent, which is iodine and potassium iodide. This forms a reddish color precipitate. Now let's see a detailed view of all this chemical test to understand the principle behind it, and once we are done it, you will be very clear how alkaloids are extracted and detected. So look at here, what we are taking is a Solanum xanthocarpum extract, which contains your solasodin, and this extract is little orange because we have taken fruit extract, to which we add your Dragendorf reagent, which is also orange. We should not get an orange coloration, which should get a precipitate, and as you can see, as they react, the orange precipitate is being formed. Similarly, you can take the Solanum extract, and to it you can add your Mayer's reagent, which is your potassium mercuric iodide, and it should give you a little pale buff color precipitate as compared to your Dragendorf. So on addition of Mayer's reagent, you will see a buff color precipitate, but note that since the extract is little orangish, you are getting a little orange color, but all in all the product, when it settles, it's buff color. Now the third reagent is your Hager's reagent, which is your picric acid. To again the Solanum extract, will add the Hager's reagent. With Hager's reagent, it should form a yellow precipitate. So let's observe. So it's a solution, and now what you get is a precipitate. So what we'll do is, when we compare the tubes, you should be able to see that Dragendorf is more orange, your Mayer should be more buff, and your Hager's reagent should be more yellowish. Just observe the difference between this orange, buff and yellow color precipitate. So from this videos, we learn how to evaluate your alkaloids or alkaloidal containing drugs. So here are few references if you want to know additionally about the alkaloids, and thank you all of you for your patient listening.